I'm Chris Tatum. Eric, Sarah, and Daniel are in my algae biodiesel group, and we're going to present on the general process. To begin with, here's an outline. We're going to start with the introduction, move on to project description, background, and show the process flow diagrams, and then give our position on the capital costs, break-even analysis, selling prices, summary, and conclusion. The project need. Gas prices are consistently on the rise and cause all kinds of problems in the extraction process throughout the world. And there's a need for a domestic supply of gasoline. In this case, biodiesel can provide that need. Our project is producing biodiesel from algae oil, and we're going to use nutrients provided by Moccasin Wastewater treatment plant here in Chattanooga. And the nutrients are municipal waste provided probably after the anaerobic digester at Moccasin. And the digester itself produces biogas. Biogas is largely methane and can be combusted to produce energy, and resulting in CO2, which is also supplied to the algae as a nutrient, along with phosphorus and nitrogen and some other chemicals needed for algae growth. Moccasin Bend currently treats about 60 million gallons per day. It's designed for about 140, and it's provided the nutrients, which are various nitrogen and phosphorus, and biogas again, to provide power and CO2. Algae production, the way we're going to go about it in our design is to use a photobioreactor. It's an enclosed reactor. It's going to be a plug flow system, tubular, much like this one over here, that sunlight can penetrate for the photosynthetic process, and nutrients are going to be in the water with the algae flowing through until they get to the end, and hopefully we'll have our large amount of algae product. And algae is a very competitive source for biodiesel. It's because of the land usage. It doesn't require near as much acreage as soybeans or some other products such as that, and it's not competitive within the food market either. So it's a good source for biodiesel. And it is a controlled environment in a photobioreactor, which is nice. A lot of open pond reactors are susceptible to other algae species and pollutants getting in the water, and you can very easily control the CO2 exposure for the algae. Once the algae is grown, you need to extract the oil. This process is known as lysing. It is cracking open the cell membranes to release the lipids that occur in algae. And lipid content in algae usually ranges rather low to maybe 15 to 20%, up to possibly even like 70%. It is a tough process to be economically feasible. It's usually very expensive to crush the algae and then to allow the oil and the water to separate. There are many methods, and the one we're considering is, what do you call that kind of grinding? Shear and plate or something? Yeah. So it shears the algae and releases the algae oil, which is carried on through the liquid effluent to later be separated. And I'm going to let Eric talk about the chemistry for biodiesel.
So biodiesel is produced from two main reactions. It's a transesterification reaction, which would be where a oil molecule, which is a triglyceride, reacts with 3 molecules of methanol to produce glycerol and fatty acid methyl esters, which are biodiesel molecules. You can also use free fatty acids through an esterification reaction. Free fatty acid is basically a third of a triglyceride molecule. You break the triglyceride into 3 pieces. Each of those pieces is basically a free fatty acid. And free fatty acids are, in low-grade oil feeds, you'd have high free fatty acid content. And if you use like waste cooking oil, for example, there'd be high free fatty acid as well. But those also react with methanol to produce fatty acid methyl esters and water. instead of glycerol. So we can sell the biodiesel for profit, glycerol can be sold for profit, and then you just have a water waste feed. Both of these reactions do require catalysis to work. So there's two types of catalysts mostly used. You have homogeneous catalyst, which means it's in the same phase as the reactant. So in this case, it is a liquid catalyst. Two subtypes under that. You can have an acidic homogeneous catalyst, which would be something like sulfuric acid, and then a basic homogeneous catalyst, which would be like sodium hydroxide. The main one currently used is sodium hydroxide, a basic homogeneous catalyst. You end up with really quick reaction rates, and you can do reactions as low as room temperature, which is a big plus. However, if there's any free fatty acids at all, the sodium hydroxide reacts directly with the free fatty acids through a saponification reaction to produce soap rather than biodiesel, which as a result leads to really expensive purification costs, and your catalyst cannot be reused because it's being reacted. So we're looking at using a heterogeneous catalyst, which in this case would be a solid catalyst. We're mostly looking at the basic nickel oxide catalyst because the university's been using that for a while now and has had pretty good results from it, but then you can also use an acidic platinum oxide catalyst, for example. The good thing of this is, being a different phase, just from gravity, you can separate the catalyst out and reuse it. So much cheaper purification, and there's no chance of any soap forming either. Another novel approach we're looking at currently is using microreactors rather than a conventional reactor size. The main reason for going to the micro scale is diffusion time, which is diffusion time equals the diffusion length squared over a diffusivity coefficient. For a conventional reactor, if you think of, for research methods, we've been using a 6 millimeter diameter stainless steel reactor. When you use something that large, even though it sounds pretty small, there's a diffusion length of 3 millimeters. That'd be from a reactant to get to a reactive surface, which would be where the catalyst is. So that's 3 millimeters, and that results in a diffusion time of 2.5 hours. Microscale, that 3 millimeters is now 50 micrometers. So the diffusion time is now 2.5 seconds as opposed to 2.5 hours. So from that alone, you can speed up processing time. Reaction times are considerably quicker. So it's hours to seconds quicker. So here's two microreactors that I've been using in my research. You have they're both 50 microns by 500 microns wide. The one on the left has a wavy flow channel, so it's 15 centimeters long in that little chip. And then the other one's just a straight 3 centimeter channel. But if we were to use microreactors, the flow rates you can normally have is about 2 microliters per minute in one reactor, just incredibly slow. And from Moccasin bin, we can produce about 38 liters per hour of algae. So if you were to go with those flow rates, we would need approximately 320,000 microreactors, which sounds like a bunch, but I'd have to talk to Dr. Jones still about this, but I'd estimate that the capital cost around about $150,000. So not for sure that'd be cheaper than a conventional reactor, but we can do things a lot quicker. So reaction time would be much less, but we're still trying to figure out the capital cost of a normal size reactor for comparison purposes. So Chris will talk to you about the biogas combustion process flow diagram and algae.
Again, as I mentioned earlier, we plan to combust the biogas produced from the anaerobic digesters at Moccasin bin. And this will begin in the digester. The biogas, methane and CO2 is produced from the algae within the digester, and it collects at the top of the digester and pressurizes there. And from there, we've actually revised this. There'll be another chamber to move the biogas to pressurize it correctly, the way we need to supply air, and then go onto the burner. From the burner, it would combust